What if I told you that one of the most mysterious space phenomena discovered in recent history wasn't found by NASA, wasn't discovered by a government observatory, but by a group of ordinary people with cameras standing under the night sky? Before we begin, make sure you subscribe to the channel and turn on notifications, because tonight's story proves that the universe still hides secrets in plain sight. This is the story of the mysterious phenomenon called Steve, and how amateur photographers accidentally uncovered something that changed space science forever. For centuries, humans have stared at the sky and believed that everything extraordinary had already been mapped, categorized, and explained. Astronomers built telescopes the size of buildings, governments launched satellites, space agencies scanned the Earth's magnetic field with advanced instruments. And yet, something slipped through. It began quietly, not in a laboratory, not in a control room, not in a classified facility. It began in the cold night air, under a sky alive with auroras. The first sightings. Across northern Canada, photographers regularly captured images of the aurora borealis. Green curtains of light rippled across the sky, dancing, shifting, alive. For those who chased auroras, this was routine. But then something strange appeared in their photographs. A narrow ribbon of light, brighter, sharper, more defined than the surrounding aurora. It wasn't green. It wasn't red. It was purple, sometimes streaked with white. It stretched across the sky like a glowing arc, almost perfectly straight, cutting through the traditional aurora like a cosmic scar. At first, people assumed it was simply a rare aurora variation. But the more images surfaced online, the more obvious it became. This was different. The Facebook group that changed science. A group of dedicated aurora photographers had formed an online community called Alberta Aurora Chasers. They were hobbyists, teachers, mechanics, nurses, students, united by their love of the night sky. They compared camera settings, shared forecasts, posted sightings. And one night, someone posted an image of the strange purple arc. The caption read, "What is this?" Dozens responded. Some thought it was lens flare. Others suggested atmospheric distortion. A few speculated about unknown aurora forms. But the arc kept appearing. Different locations, different photographers, different cameras. Same phenomenon. And then, jokingly, someone named it. Let's just call it Steve. The name stuck. Why Steve? The name came from a children's animated movie where characters give a mysterious creature a random human name because they don't know what it is. It was a joke, a placeholder, but it made the phenomenon easier to talk about. Did you see Steve last night? Steve was bright over Edmonton. And slowly, the joke became serious, because scientists started paying attention. Enter the researchers. Researchers studying auroras monitor charged particles interacting with Earth's magnetic field. The aurora borealis well is studied. Solar wind hits Earth's magnetosphere. Particles excite atmospheric gases, and light is emitted. But Steve didn't behave like normal aurora. When researchers compared satellite data with timestamps of photographs, they found something astonishing. Steve was linked to a phenomenon called a subauroral ion drift, a fast-moving river of superheated charged particles in the upper atmosphere. Temperatures in the ribbon region were thousands of degrees hotter than surrounding space. It wasn't just light. It was energy. Extreme energy. And it had been happening for decades. Undocumented. Unnoticed. Until photographers captured it. A scientific shift. For the first time in history, a major atmospheric phenomenon had been identified not by professionals, but by civilians. That shook assumptions. Space science is precise, controlled, instrument-based. Yet here was proof that collective observation, hundreds of cameras pointed upward, could reveal what satellites overlooked. Steve wasn't rare. It was simply misunderstood. What makes Steve different? Unlike traditional auroras, Steve forms at lower latitudes. It appears as a thin arc rather than curtains. It emits purple and white light. It moves differently. It aligns with specific magnetic disturbances. And sometimes beneath Steve, green picket fence structures appear, vertical light bars that seem almost artificial. Photographers describe them as like a glowing zipper across the sky. No one had predicted that. No textbook mentioned it. The night that went viral. In early 2016, images of Steve exploded online. One photograph showed a massive purple ribbon stretching horizon to horizon across Alberta's night sky. The image was shared thousands of times. Scientists could no longer ignore it. Formal studies began. NASA satellites were cross-referenced. Ground sensors were examined. Magnetometers were reviewed. And slowly, the pieces aligned. Steve wasn't alien. It wasn't artificial. It wasn't paranormal. It was a new category of upper atmospheric phenomenon. Why it matters. Steve revealed something deeper than just a new light in the sky. It proved that the scientific process is not closed. Discovery is not limited to laboratories. Sometimes curiosity is enough. An amateur photographer with a tripod and patience changed the way we understand near-Earth space. That realization inspired a wave of citizen science projects. People began monitoring meteors, tracking satellites, reporting atmospheric anomalies. Because if Steve existed unnoticed for so long, what else might be waiting? The emotional side of discovery. Many of the original photographers described the moment scientists confirmed Steve's uniqueness as surreal. They weren't trying to make history. They just loved the sky. One member said, "We went out to take pictures of beauty. We didn't expect to find something new." There is something powerful about that. In an age where it feels like everything has been mapped, labeled, explained, Steve reminds us that wonder remains. The universe still surprises us. The Earth's magnetosphere is invisible. Solar winds are unseen. Charged particles race silently above our heads. And sometimes, under the right conditions, those invisible forces paint the sky in purple fire. Steve appears quietly, without warning, without schedule, and then fades, leaving behind questions. A new chapter in skywatching. Since its identification, scientists continue to study Steve. Advanced satellites track ion drifts more precisely. Ground cameras monitor geomagnetic storms. Researchers refine atmospheric models. But the origin story remains unique. Not a classified program, not a government lab.
The strange thing about
a Facebook
Steve
group,
wasn't just
a
how
joke
it
name,
looked. It
a
was
purple
where
ribbon
it
in the sky.
appeared.
And if you've stayed
Traditional
this far into
auroras
the story,
usually form
remember,
in oval-shaped zones
sometimes
around
the
the
greatest
magnetic
discoveries
poles.
don't begin with
Scientists
billion-dollar
have mapped
equipment.
those regions carefully.
They begin with curiosity.
They know when to expect geomagnetic storms. They know how solar activity affects Earth's atmosphere. But Steve didn't follow the usual rules. It appeared farther south than expected, sometimes hundreds of miles below the normal auroral oval. That alone was enough to create confusion. If it wasn't a traditional aurora, then what was powering it? The hidden river in the sky. When researchers dug deeper into satellite data, they discovered something extraordinary. High above the Earth, about 250 miles up, flows a narrow stream of charged particles. These particles move at incredible speeds, sometimes exceeding 13,000 miles per hour. This stream is called a subauroral ion drift. Before Steve, this phenomenon was known, but not visually connected to visible light emissions. Scientists knew the ion drift existed because instruments detected changes in temperature and velocity, but no one realized it could produce visible light. That connection changed everything, because suddenly something invisible had become visible, and once something becomes visible, it becomes undeniable. The temperature mystery. Data showed that inside the Steve arc, atmospheric temperatures could rise by thousands of degrees, not hot like fire, hot like plasma. And yet, from the ground, it looked delicate, thin, soft, almost peaceful. That contrast fascinated researchers. How could something so visually calm contain so much energy? The answer lies in charged particles colliding with atmospheric gases. When particles accelerate along magnetic field lines, they transfer energy into the upper atmosphere. Under the right density and speed conditions, that energy excites molecules enough to emit light. But Steve's emissions were different from classic auroras. Auroras glow green because oxygen atoms emit light at specific wavelengths. Steve's purple tone suggested a combination of nitrogen emissions and thermal effects. It wasn't just particle precipitation, it was heat-driven emission, a glowing scar caused by energy friction. The photographers who stayed up. While scientists analyzed data, photographers continued their ritual. They drove into rural areas, waited in freezing temperatures, set up tripods, watched the sky. Many described Steve as unpredictable. You could forecast auroras using solar wind data, but Steve, it required specific geomagnetic conditions, not too weak, not too strong, a narrow window. And sometimes it would appear suddenly, slicing across the sky like a luminous blade. Some nights it was faint, other nights it dominated the sky. One photographer described it as, it looked like someone had drawn a glowing line across the universe. Global sightings. As awareness grew, reports began emerging beyond Canada, northern United States, Scotland, New Zealand. Images flooded social media. Different hemispheres, different seasons, same purple arc. This confirmed something critical. Steve was not local, it was global. That realization transformed the scale of the discovery. What began as a regional curiosity became a planetary phenomenon. Scientific debate. At first, not all researchers agreed. Some argued Steve was simply a type of proton aurora. Others believed it was a rare manifestation of known processes. Scientific discovery often involves disagreement, peer review, skepticism, testing. But the more data accumulated, the clearer it became. Steve did not fit neatly into existing categories. So scientists created a new classification, not just aurora, but a distinct phenomenon, and that is rare in modern atmospheric science. The power of citizen science. What makes this story powerful is not just physics, it's participation. The original photographers were not professionals, but they were observant, consistent, collaborative. They time-stamped images, shared coordinates, cross-referenced sightings. Without realizing it, they created a distributed observation network. Hundreds of cameras, thousands of miles apart, operating simultaneously. This decentralized monitoring system was more flexible than many institutional setups. And it proved something important. The boundary between amateur and expert is thinner than we think. Curiosity is a powerful instrument. The emotional impact. When the phenomenon was officially recognized in scientific papers, many original observers felt a quiet pride. Not fame, not celebrity, just validation. Their questions had mattered. Their photographs had meaning beyond beauty. And for some, it changed careers. A few went back to school, studied atmospheric science, entered research fields. Because sometimes discovery doesn't just change textbooks, it changes lives. A reminder of the unknown. We often assume that modern science has mapped Earth completely, but Steve is proof that our planet still holds surprises. The magnetosphere is invisible to our eyes. Solar wind is intangible. Charged particles cannot be seen. Yet when conditions align, the invisible becomes visible. And when it does, we are reminded. We are still learning. The night sky as a laboratory. Steve has encouraged new monitoring programs. Scientists now coordinate with photography groups. Aurora chasers share real-time updates with researchers. Satellites are cross-checked against ground observations more frequently. This collaboration has strengthened space weather research. And space weather matters, because geomagnetic storms can disrupt satellites, GPS systems, power grids, communication networks. Understanding several phenomenon is not just beautiful, it's practical. Why it feels mysterious. Even with scientific explanation, Steve still feels mysterious. Because it appears suddenly, because it stretches silently across the stars, because it looks almost artificial. A straight glowing line cutting through the sky. There is something deeply human about that reaction. We are wired to interpret unusual sky events as significant. For most of history, unexplained lights meant omens. Today they mean research, but the emotional response remains. Awe, curiosity, smallness. The name that stayed. Scientists eventually gave Steve a formal backronym, Strong Thermal Emission Velocity Enhancement, but no one calls it that. The nickname stayed. Steve. A reminder that discovery doesn't have to be rigid. It can begin with humor. The bigger question. If a visible atmospheric phenomenon went undocumented until the 21st century, what else might we be missing? Transient events, short-lived energy patterns, atmospheric interactions we haven't connected yet. Our planet exists in constant dialogue with the sun. Invisible forces are always moving above us. Most of the time we don't notice, until something glows. And that is perhaps the most powerful part of the story. Steve was always there, flowing, heating, moving through magnetic corridors. But without observers, it remained unnamed.
Mapped constellations. Sailors navigated by stars. Scientists measured planetary motion with mathematical precision. And yet, in the 21st century, a glowing river of plasma stretching across the night sky remained unnamed. That realization forces a quiet question. How many other phenomena pass above us unnoticed? The invisible shield around Earth. To understand Steve fully, we have to step beyond the atmosphere, far beyond the clouds, beyond aircraft, beyond satellites. Earth is wrapped in an invisible magnetic shield known as the magnetosphere. This shield protects us from the sun's charged particles, a constant stream known as solar wind. Without it, the atmosphere would slowly erode. Radiation levels would rise. Life as we know it would struggle to exist. Most of the time, this magnetic shield deflects solar wind quietly. But during solar storms, the interaction becomes dramatic. The shield compresses, energy builds, particles accelerate. And when those particles collide with atmospheric gases near the poles, auroras are born. But Steve forms differently. It is not simply particles raining downward. It is a fast-flowing river of ionized plasma sliding horizontally across magnetic boundaries, a boundary most people never knew existed. The magnetic boundary. There is a region in the upper atmosphere where two electrical currents meet. On one side, the auroral oval. On the other, quieter magnetic zones. Between them lies tension. When geomagnetic conditions intensify, this boundary sharpens. Electric fields strengthen. Plasma accelerates. And in that narrow corridor, Steve appears.
Think of it like friction, like wind rushing through a mountain pass, except instead of air, it's charged particles moving at extreme velocity. The night of maximum intensity. In 2018, during a particularly strong geomagnetic storm, photographers across North America reported something extraordinary. Steve was brighter than ever, thicker, more defined. Some images showed the purple arc stretching from horizon to horizon, almost perfectly straight. Beneath it, a structure appeared, vertical green streaks, evenly spaced, like glowing fence posts. Scientists later nicknamed it the picket fence. This secondary structure stunned researchers. It suggested complex electromagnetic interactions happening simultaneously, not just heating, not just drift, but layered processes. The sky was more dynamic than models predicted. The human reaction. When people see auroras, they often describe beauty. When people saw Steve for the first time, many described confusion. It looked artificial, like a laser across the sky, like a crack in reality. That psychological reaction is important. Our brains are wired to recognize patterns. Auroras ripple and dance. They look organic. Steve, by contrast, appears structured, linear, sharp, almost engineered. That contrast triggered unease in some observers. Even after scientific explanation, that emotional reaction remained. A shift in observation culture. After Steve's recognition, something changed in the global skywatching community. People began paying closer attention, not just to auroras, but to everything unusual. Rare halos, atmospheric arcs, transient luminous events. Online communities grew. Amateurs collaborated with professionals in real time. Data sharing accelerated. And suddenly, science felt less distant. Satellites and synchronization. One of the most critical breakthroughs came when researchers matched ground photographs of Steve with satellite passes. The European Space Agency's swarm satellites were flying overhead during some sightings. When they reviewed data from those moments, instruments recorded extreme ion drift velocities, elevated electron temperatures, strong electric fields. The alignment was undeniable. The purple arc on the ground matched a ribbon of energy in space. For the first time, the phenomenon had dual confirmation: visual, instrumental. The fragility of knowledge. There is a humbling lesson in this story. Scientific knowledge is powerful, but it is not complete. It evolves. Sometimes it requires new instruments. Sometimes it requires new perspectives. And sometimes it requires someone simply asking, "What is that?" That question, asked without ego, without assumption, can unlock entire fields of study. The broader implications. Understanding Steve improves space weather modeling. And space weather is not abstract. A severe geomagnetic storm can disrupt power grids, satellite communications, airline navigation, military systems. By studying subarauroral ion drifts more counterly, scientists refine their predictive capabilities, which protects infrastructure and lives. So the purple ribbon in the sky isn't just beautiful. It's informative. The silence of space. Perhaps the most haunting part of this story is this. Steve makes no sound. No rumble, no crackle, no warning. It glows silently, 250 miles above Earth. A river of plasma, invisible most of the time. Only under precise conditions does it reveal itself. And when it does, it lasts minutes, then disappears, like it was never there. Rediscovering wonder. In a world dominated by screens and satellites and algorithms, Steve reminds us that looking up still matters, that not everything is automated, that human curiosity still has value. There is something poetic about it. A group of photographers chasing beauty stumbled into discovery. They weren't searching for anomalies. They were chasing light, and found science. The future of sky discoveries. Since Steve's identification, research into transient atmospheric events has intensified. Scientists now monitor subauroral polarization streams, magnetosphere-ionosphere coupling, thermospheric heating anomalies. And with better instruments, more surprises may come. Because if a visible phenomenon like Steve could remain unnamed until recently, what about phenomena that are invisible? The final reflection. Steve is not rare in the cosmic sense. It is part of Earth's magnetic heartbeat. But it feels rare. Because we named it. Because we noticed it. Because we were paying attention. That is the quiet triumph of the story. Not the physics. Not the plasma. But attention. Curiosity. Observation. And maybe tonight, There
somewhere
is a
above
moment
the northern horizon,
just before Steve
a thin
appears,
purple arc is forming
when the
again.
sky feels ordinary.
Silent.
The stars
Fast.
sit quietly.
Unnoticed
the
by
air is
most.
still. Nothing
somewhere,
suggests that
someone is setting up a
250 miles
tripod,
above, energy
watching,
is building.
waiting,
Most people never
asking,
notice that moment.
what is that?
But the photographers do. They study solar wind forecasts. They track geomagnetic indexes. They read data most people have never heard of: KP index, BZ orientation, solar flux levels. Because Steve does not appear randomly, it requires alignment, a specific configuration of solar wind pressure, a southward turning of Earth's magnetic field, a transfer of energy from space into the upper atmosphere. And when those conditions converge, something invisible begins to accelerate. Energy transfer. The sun constantly emits charged particles, protons and electrons, moving at high speeds. When those particles reach Earth, they encounter the magnetosphere. If the magnetic orientation is favorable, energy transfers through a process called magnetic reconnection. Think of it like tension snapping and reconnecting. Energy stored in magnetic fields suddenly releases. That energy travels along magnetic field lines toward the poles. Most of it feels auroras, but some of it moves sideways, along the boundary between auroral and subauroral regions. And that sideways motion creates extreme electric fields. Those electric fields accelerate ions horizontally, faster than expected. That horizontal river of plasma is what we call a subauroral ion drift. And when the velocity and temperature reach critical thresholds, Steve glows. The precision of the arc. One of the most striking characteristics of Steve is its shape. Auroras dance. They ripple like curtains in wind. Steve is different. It is narrow, straight, defined, almost surgical. That shape reflects the precision of the electric field boundary. The phenomenon exists in a thin corridor. Too far north and it merges into auroral chaos. Too far south and it dissipates entirely. It lives on the edge, literally. The data that shocked scientists. When swarm satellites flew directly through Steve's region, instruments recorded ion speeds exceeding 6 kilometers per second, temperature increases of over 3,000 degrees Celsius, strong electric field gradients. Those numbers were unexpected. The upper atmosphere is typically cold and sparse, but inside Steve, it became energized, turbulent, dynamic, and yet from the ground, observers described it as calm. That contrast between violence and beauty is one of the most fascinating aspects of the phenomenon. The psychological weight of discovery. For the amateur photographers, something subtle changed after the scientific validation. Before, they were hobbyists. After, they were contributors. Some felt intimidated. Suddenly, scientists were contacting them, requesting timestamps, asking for raw image files. Others felt empowered. They realized they were part of something bigger, a living collaboration between citizen observers and institutional science. It blurred the line between professional and amateur, and that shift may be one of Steve's greatest legacies. A broader cultural impact. News outlets covered the story. Headlines emphasized the nickname, the mysterious Steve in the sky. The humor of the name made the phenomenon accessible. People who would never read a scientific paper clicked on articles because of curiosity, and through that curiosity, they learned about magnetospheres, solar wind, plasma physics, space weather. Steve became a gateway, a purple ribbon that pulled public attention toward complex science. The fragile balance of Earth and Sun. Every second, Earth is bombarded by energy from the sun. Most of it never reaches us. The magnetosphere deflects it, absorbs it, channels it. But during solar storms, that balance tightens. Energy floods in faster than usual. The magnetosphere compresses. Currents intensify. And the upper atmosphere becomes a stage. Auroras flare. Radio signals fluctuate. Satellites feel drag changes. Steve is one visible signature of that cosmic dialogue. A reminder that Earth is not isolated. It is immersed in space weather. The night the forecast failed. There were nights when forecasts predicted strong auroras. Photographers rushed out. Tripods planted. Cameras ready. But instead of curtains of green, a sharp purple arc appeared. Unexpected. In regions where auroras weren't forecasted strongly. That unpredictability forced scientists to refine models. It suggested that subauroral dynamics were not fully captured in predictive systems. In other words, our understanding was incomplete. The role of technology. Modern digital cameras played a crucial role in Steve's recognition. High-sensitivity sensors capture faint light that human eyes struggle to detect. Long exposures reveal details invisible in real time. In some cases, photographers did not even realize they had captured Steve until reviewing images later. Technology amplified observation. It extended human vision. Without modern sensors, Steve might still be unnamed. A philosophical reflection. There is something humbling about this. Despite satellites orbiting Earth, despite telescopes scanning galaxies, despite decades of research, a visible atmospheric phenomenon remained uncategorized. It suggests that knowledge is not only about instruments. It is about attention, curiosity, persistence, the silent conversation above us. Imagine standing beneath Steve, the sky dark, stars steady, a purple arc cutting across constellations. Above that arc, invisible rivers of charged particles rush at incredible speed. Electromagnetic fields fluctuate. Plasma heats. Ions collide. And yet on the ground there is silence. The scale difference is staggering. Massive energy. Tiny observers. It reframes our perspective. Could there be more? Scientists now believe that other subtle atmospheric phenomenon may exist undetected. Short-lived, rare, condition-dependent. Perhaps they are too faint, too fast, too geographically limited. Or perhaps we simply haven't recognized them yet. Steve teaches an important lesson. Recognition requires pattern awareness. And pattern awareness often begins outside formal systems. The future of citizen science. Following Steve's discovery, structured citizen science networks expanded. Smartphone apps now allow observers to log aurora sightings in real time. Photographers share coordinates instantly. Data flows more freely. The collaboration model is stronger than ever. Steve wasn't just a discovery. It was proof of concept. Proof that distributed observation works. A new kind of explorer. Explorers once sailed oceans, then climbed mountains, then traveled to space. Now exploration sometimes means standing still, looking up, paying attention. Steve redefined exploration in a quiet way. You don't need a spacecraft. You need patience. The emotional core. At its heart, this story is about wonder. About the moment when something familiar becomes unfamiliar. When the sky you thought you understood reveals a new secret. And in that moment you feel small, but also connected. Because the universe just showed you something new. And somewhere tonight, under cold northern air, someone is adjusting their camera settings. ISO high, exposure long, lens focus to infinity. Waiting. Because maybe, just maybe, Steve will appear again.
The longer scientists studied Steve, the more they realized something unsettling. This phenomenon had likely been happening for centuries, long before cameras, long before satellites, long before social media groups. Indigenous communities living under northern skies may have witnessed it, but without the framework of modern magnetospheric science, it would have blended into the broader tapestry of auroral mythology. How many times had Steve appeared, unnoticed by science? How many times had it sliced across the night sky while no instruments were pointed at it? A boundary we didn't understand. The magnetosphere is often described as a shield, but that description is too simple. It is not a solid barrier. It is dynamic, elastic, shifting constantly under solar pressure. When the solar wind intensifies, the dayside magnetosphere compresses. Energy is stored in Earth's magnetic tail, the long extension of magnetic field lines stretched away from the sun. Eventually, that energy must go somewhere. And sometimes, instead of releasing in chaotic auroral storms, it channels into narrow, concentrated streams. That channel is where Steve lives, a boundary layer, a place of tension, a place where small changes in solar wind can create dramatic consequences. The geometry of the sky. Steve often appears as a straight or slightly curved arc. That shape reflects the geometry of Earth's magnetic field lines. Magnetic lines are not visible, but they guide charged particles. The arc traces the invisible architecture of our planet's magnetic environment. When you look at Steve, you are looking at geometry, at invisible structure made visible, at physics painted across the night. When beauty becomes data. Before Steve, most people who photographed auroras were chasing art. They wanted color, motion, atmosphere. After Steve, every image became potential data. Timestamps mattered, coordinates mattered, orientation mattered. Some photographers began recording magnetic index levels with their photos. They logged weather conditions, solar wind parameters, geomagnetic readings. The sky was no longer just a canvas. It was a laboratory. The first peer-reviewed paper. When researchers formally published their findings, the scientific community paid attention. Because this wasn't speculation, it was confirmed by ground-based imagery, satellite instrumentation, magnetic field data, plasma measurements. And the conclusion was clear. Steve was associated with intense subauroral ion drift and elevated temperatures not previously connected to visible emissions. That meant new models were required, new calculations, new simulations. It expanded the textbook. The power of naming. Names shape perception. If Steve had been labeled subauroral thermal plasma arc, it might never have captured public imagination. But Steve? That invited curiosity. It made the phenomenon approachable, human. And ironically, that accessibility amplified scientific interest. Sometimes simplicity spreads faster than precision. A new awareness of space weather. Steve's discovery came during a time when awareness of space weather risks was increasing. Scientists warned that extreme solar storms could disrupt global infrastructure. In 1859, the Carrington event caused telegraph systems to spark and fail. If a similar storm occurred today, satellites and power grids could suffer massive damage. Understanding every layer of magnetospheric interaction matters, even narrow plasma rivers, even purple arcs, because they are pieces of a larger system. The fragility of prediction. Space weather forecasting remains imperfect. Solar flares are unpredictable. Magnetic reconnection timing is complex. Plasma behavior is chaotic.
Steve represents a layer of complexity previously underappreciated. It forces researchers to ask, are there other boundary phenomena we haven't categorized? Are our models too simplified? Is the magnetosphere more structured than we assumed? Each question pushes research forward. The emotional weight of the sky. For many who have witnessed Steve, the memory stays vivid. The moment the purple arc appears, the realization that it is different, the silence beneath it. Some describe feeling small, others describe feeling privileged, as if the sky revealed something rare. And in a way, it did, because recognition is rare, seeing is rare, understanding is rare. The intersection of technology and curiosity. Modern science often depends on expensive equipment, but Steve's discovery shows that distributed curiosity can rival centralized systems. Hundreds of observers across continents formed a real-time monitoring network without formal structure. They were connected by shared interest, and that connection became powerful. This is the future of observational science. Collaborative, decentralized, participatory. The quiet revolution. Steve did not change astronomy headlines overnight. It did not revolutionize astrophysics, but it quietly reshaped atmospheric science. It proved that our planet still holds surprises, and it reminded researchers to look again at data already collected, because sometimes discovery isn't about new measurements, it's about new interpretation. The night sky is not finished. We often talk about exploring space as if it lies far away, but Steve reminds us that space touches Earth constantly. The boundary between atmosphere and space is active, alive, dynamic, and occasionally visible. Perhaps the greatest mystery isn't distant galaxies. Perhaps it is the invisible forces moving just above our heads. And somewhere tonight above the Arctic Circle, solar wind pressure may be building again, magnetic lines may be tightening, plasma may be accelerating, and a narrow purple arc may be preparing to appear, not as a spectacle, not as a warning, but as a reminder that discovery is not over, that the sky is not fully understood, that curiosity still matters.